might have to go now. 4 or 5 take this action.
HDMI. All right, let's get started. So last lecture on Monday, we left off on kind of a somber note. We learned that we could use value functions and Q functions to do reinforcement learning without an explicitly represented policy. But then we learned that if we go and try to do this with deep neural networks or any other kind of function approximator, as opposed to a tabular representation, we can't actually get an algorithm that converges. So theoretically, we can't show that it's a convergent procedure, which means that we can't really say anything concrete about it theoretically. So today we're going to learn how we can ignore all of that and build effective Q-learning algorithms with deep neural nets in practice, and then you'll all do this for homework 3. So we will actually discuss a little bit of intuition for why that's not entirely crazy. And a lot of this is going to kind of involve more the practical side of deep RL, as opposed to Monday, which involved kind of the more theoretical side. All right, a few class notes before we begin. Homework 2 is due next Monday. Hopefully all of you have already started on homework 2. If you haven't, you really should. It's probably going to be a little tougher than homework 1, so don't leave it to the last minute. Project proposals are due on September 25th, which is today. So hopefully all of you are writing your project proposals, and we'll have those ready by the end of the day. Please remember to submit them both through Gradescope and through the course CMT website. The CMT website is so that you can have peer review from your peers who will actually read your proposal and make suggestions. The proposal is not graded based on what your peers think of it. That's more for your feedback, but it's very important feedback because you want to get an idea for kind of whether the scope of your proposal is good, whether the ideas are solid, whether it's likely to work. Hopefully your peers can comment on that. So do make sure to submit to both Gradescope and CMT so you can get a grade through Gradescope and get comments from your peers through CMT. All right, today's lecture. Today we're going to talk about how to make Q-learning actually work with deep neural networks. We're going to get kind of this generalized view of Q-learning algorithms. We're going to see how we can instantiate different versions of that generalized view to get actual practical algorithms we can use. We'll talk about some tricks for improving Q-learning in practice. And we'll also conclude with a little bit of a discussion about how you can do Q-learning for continuous action spaces, which has a few unique challenges. So the goals for today's lecture, will be to understand how to implement Q-learning so that it can be used with complex function approximators, like deep neural networks, to understand how to extend Q-learning to continuous actions, and more generally just to understand how to make Q-learning work well. A lot of the things that we'll cover in today's lecture will be very relevant for you for homework 3, so do make sure to pay close attention there. You'll probably need to implement some of these things. All right, so first let's recap some of the things that we covered on Monday. So on Monday we went through this derivation where we started with actor-critic, then we got rid of the actor and we're left with just the critic. And since calling it the critic-critic algorithm is kind of boring, we called it Q-learning or fit-a-Q iteration. And we saw how we could derive an algorithm that could actually optimize expected reward, at least in the tabular case, without explicitly representing a policy, but just by keeping track of a Q function. So this fit-a-Q iteration algorithm up above, this is what we ended up with on Monday. We can think of it graphically in our favorite diagram as basically updating the Q function in the green box by assigning the Q values here, and then in the blue box, the way it recovers a better policy is just by using the argmax policy. So there's no explicit pi. The pi is just recovered from the Q using the argmax. So the general version of this algorithm, the fit-a-Q iteration algorithm up here, basically has 3 steps. You collect some data using some policy, and we talked on Monday about how this policy could be the greedy policy, but in practice it's better to make it a little bit more random to induce some exploration because the greedy policy is deterministic. So we collect some data, and we can decide whether to collect a little bit of data or a lot of data, so that's a design decision. And then we compute target values as the reward at each sample plus the discount times the max of the Q value at the next state. And this bit, this max, basically allows us to make this an off-policy algorithm, meaning that we don't care which policy the transitions came from, although in practice we of course want them to cover the space well. And then the third step is when we actually train the network, train the Q function approximator by minimizing the difference between the Q values and the target values y that we computed in step 2. And in the most general case, we can alternate step 2 and 3 k times, and we can go back and collect more data if we so choose. If we instantiate a version of this algorithm where we take exactly one gradient step in step 3 and set k equal to 1, and collect only one data point in step 1, basically set all the parameters to 1, then we actually recover the online Q-learning algorithm. So the online Q-learning algorithm takes one action, collects one transition, SAS prime R, computes one target value on that one transition, and then takes one gradient step using the difference between the current Q value and the target that it just computed. So this online version of the Q-learning algorithm, this is also sometimes referred to as Watkins Q-learning, named after the person who first proposed it. When someone says Q-learning or online Q-learning, this is usually the algorithm that they have in mind. Does anybody have any questions about fit-a-Q iteration or online Q-learning? Okay, good. So now let's talk a little bit about why online Q-learning is kind of not very good. So what's wrong with online Q-learning? Well, we saw on Monday kind of the theoretical view about what's wrong. What's wrong is that you can't prove that it converges. Does anybody have any ideas, kind of more practical, kind of intuitive notions about what might be wrong? Just from looking at the structure of this pseudocode, what might go wrong if you try to do this with a deep neural network to represent Q phi? Any ideas? Any guess? Any wild guess? Yes.
If your initial policy is really bad, maybe you'll never learn.
Okay, good. So maybe your initial policy is pretty bad, so the data you collect in step 1 might never visit states with high reward, so that would be a problem. So we have to be a little careful in choosing the right policy for step 1. So even though it says take some action, you really do have to be a little bit clever in making sure you actually take actions that will visit high reward states. So that's called exploration. And we talked about that a little bit on Monday, but we'll talk about it a lot more later on in the course. Any other ideas? Yeah?
It's like just intuition. I feel like this kind of update process is a little bit like similar to GANs. And then GANs usually get into when we're like
Yeah.
this too,
Okay.
you know what I mean?
So let me explain this comment to the rest of the class. So the comment was, this kind of looks a little bit like a GAN, and GANs are really hard to train. So for those of you that don't know, GANs stands for Generative Adversarial Networks, which are a type of generative model where there's an adversarial game played between two networks. Here there's only one network, but there's a little bit of truth to that. It's a little bit more obvious in an actor-critic algorithm, because there you actually do have two models where one is trying to maximize the other. A little bit less obvious why that's the case in Q-learning, but it does have some elements of that. So this is maybe a longer discussion for after class. Here is a thought. When we talked about actor-critic, we talked about how we could formulate an online version of actor-critic that looked a little bit like this, but had to be on policy. And that one, we needed to do a bunch of stuff to really make it work. Does anybody remember what we needed to do to make online actor-critic work? Yeah. Batches instead of single samples, right? So look over here. We collect one sample, we calculate a target value, and then we take a gradient step using just one sample. Training a deep neural network with one sample for every gradient step is actually quite difficult. So kind of the basic formulation of stochastic gradient descent does prescribe using one sample at a time, but in practice, that usually has a little too much variance. So when we actually train deep neural nets, for example, for supervised learning, we usually use mini batches of size greater than 1. So we'd really like to do that for Q-learning as well, because taking these gradient steps for a large neural net Q phi with a batch size of 1 is going to make it really hard to optimize. There's another problem, which is a little bit more subtle. So remember when I talked about how Q-learning doesn't converge in theory? Looking at the form of this update in step 3, it might seem at first a little bit puzzling why this wouldn't converge, because it kind of just looks like we're doing gradient descent, right? This is a derivative. We take the derivative of some loss. It looks a lot like actually the squared loss. There should actually be a square there. So it seems like it's just gradient descent, right? You compute the derivative of some loss, take a step in the direction of that derivative, you should get better. Why is this not just gradient descent? What's the, yeah?
Moving target?
Yeah, it's a moving target. So look at this y. This y is calculated using Q phi. Now when we calculate the gradient here, we ignore the fact that this y depends on phi. So that's not actually gradient descent, even though it looks like there's a little derivative operator. This isn't really the derivative of the difference between Q phi and this full target value, because the target value itself depends on Q phi. So that means that Q phi kind of goes after the target, but the target keeps moving away from it. In fact, in practice, if you try to run Q-learning, for example, for homework 3, and you print out the loss function here, you'll actually see that the loss goes up. You'll actually see your agent getting better, the Q function will get better, you'll get higher rewards, but that loss will go up. And in supervised learning land, this will be really bizarre, but in Q-learning land, this is actually perfectly normal. So Q-learning is not gradient descent. If we were to actually plug in the definition of y into this equation, we would see that there's no gradient that actually flows through this bit. So we hit this with dq d phi evaluated at si ai, but if we want to have actual gradient descent, we have to push a gradient through this thing also. That's very difficult because there's a non-differentiable max operator. It's actually very difficult for yet another reason. Even if you can differentiate through the max, it still won't work. That's a much longer story, so if you want to learn about that, ask me in office hours. But as classically formulated, this is most definitely not gradient descent, because it is not the correct gradient. And of course, the other issue is that you have a batch size of 1 here, and even worse than that, on successive gradient steps, your samples are highly correlated because the way that you're collecting them is by executing some policy in an environment. So the sample I saw right now will strongly correlate with the sample I'm going to see 1 second from now. So in regular SGD, SGD will converge if you're actually doing gradient descent and you draw samples IID from some distribution. These samples are most certainly not IID. Temporally sequential things are not IID if you actually have a sequential decision-making problem. So there are 2 major reasons why this is very much not gradient descent. And these 2 issues are things we can actually try to mitigate a little bit. So let's work on those correlated samples first, because that's a little bit easier to deal with. So the problem essentially is that sequential states are very strongly correlated. The other problem is that your target value is always changing. But let's talk about the correlated thing first. So imagine this is your trajectory. Essentially what happens if you run online Q-learning is that you see a few samples along the trajectory, you take some gradient steps on those samples, so you kind of locally overfit to these guys. Then you see some more samples, they're also close together, you locally overfit to those, and so on and so on. And by the time you get over here, you've probably forgotten what was going on over here. So instead of actually learning something, you're just kind of repeatedly overfitting to your local neighborhood and not actually getting anywhere. And that's a problem. So we could solve this problem in a few ways. One of the ways we could solve it is by using the same trick that we used for actor-critic. So we could actually implement a parallel version of Q-learning where you have multiple workers and you do updates like this. You're still correlated in time, but at least now you have batches of size more than one. So that's the same as for actor-critic. So if it was good enough for actor-critic, surely it's good enough here. But it still doesn't fully resolve the correlation problem, and while for actor-critic we didn't have any other choice because actor-critic had to be on policy, with Q-learning we actually have a better option. So you could do the parallel thing, but there's actually a much simpler and much better solution to this issue that we can use for Q-learning that was not available to us for on-policy actor-critic. So here's what we can do. It's called a replay buffer. Here's the basic principle. If we go back for a minute to the fit Q duration algorithm, which is what we kind of initially derived, and then our online Q-learning is basically a special case of this. Let's think a little bit about step one in the fit Q duration algorithm. Step one says collect a data set using some policy. It doesn't have to be your latest policy. It can be an older policy. And of course, the online Q-learning is a special case. So any policy will work. You want a policy with broad support, because if your policy only ever visits unrewarding states, then you won't learn anything about the important states. But so long as you have broad support, you can use a wide variety of different policies. So what if instead of actually literally collecting data from the environment, you just loaded data from some buffer that had been collected using a different policy? Right? The algorithm doesn't care whether the data is loaded from a buffer or actually collected from the environment. It's the same data either way. So instead of literally interacting with the environment and collecting a batch of data using, let's say, an epsilon greedy version of your latest policy, just load up a batch of data from some past policy that you had. And you can reload it multiple times and reuse it. So the kind of mental model that you can think of for fitted Q iteration in this case is that you have this data set of transitions. You're running these steps 2 and 3 on that data set, loading a little batch every time. You can still use one gradient step here if you want, or you can use multiple steps. And then periodically, you can also go out and kind of refill your buffer with some real-world transitions, but those aren't necessarily the transitions that you'll immediately use for learning. Those transitions just get added to your buffer, and when you actually have to train, you just choose a little batch from your buffer. So this will make it so that samples are no longer correlated. All I've really done now in the Q-learning algorithms is I just replace step 1 with sample a batch from your buffer B. So instead of actually interacting with the world and training on the latest data, you sample a little batch, and in particular that batch can be greater than 1 in size. So now you have more than one sample, and the samples are decorrelated because they come from some big buffer in the past rather than a sequential process. So you have more than one thing here, so you're summing over your little batch. That gives you a better lower variance gradient, and the samples are not correlated. So where does the data come from? Well, you need to periodically feed your replay buffer, and you can, again, do that however you want. So here's that mental model again. You have your data set of transitions. You have your off-policy Q-learning process that's sort of crunching away on this data set. And then you have the world over here, and periodically you go out and you grab some more data from the world. And when you do that, maybe you'll use an epsilon greedy version of your latest policy, but you don't immediately train on that data, you just add it to your buffer, and then you keep crunching away on whatever is in there. So this ensures that when you're actually training, you sample transitions in an IID way from your buffer, which decorrelates them and allows you to use a batch size greater than 1. And then you can still collect more data to make sure to periodically refresh this thing. For example, if your initial policy is bad and never visits high reward states, then refreshing the buffer periodically ensures that as your policy gets better, you actually put some of those good states in your buffer and train on them. Does anybody have any questions about the replay buffer? Okay, pretty simple idea. So we can put this together and get a full Q-learning algorithm with the replay buffer. So you collect a data set using some policy, you add it to your buffer, and there's a choice to be made about how much data you collect here. So that's this step. Then you sample a batch from the buffer. Then you take a gradient step on that batch. You repeat this some number of times, maybe 1 time, maybe 100 times. K equals 1 is pretty common, but using larger values of k can be more efficient. And then you go back out and collect some more data. All right, so that deals with the correlation problem and gives us a batch size of greater than 1, but we still have this problem with chasing a moving target. We still have this problem in step 3 where we're not really doing gradient descent, and the target values are actually affected by these gradient steps, but the pseudo gradient that we have is not actually aware of that. So we've solved the correlation problem. Now let's deal with the other problem. Let's think about how Q-learning actually relates to regression. So it kind of looks like the gradient of a regression loss, but isn't. In the fitted Q iteration algorithm, it's made a little bit more explicit. In the fitted Q iteration algorithm, in step 3, it's actually written out as a regression problem. It says, we'll find the phi that actually minimizes this regression loss. And here in step 3, in the more online method, we're just saying, well, let's just do one gradient step of that. So in the fitted Q iteration algorithm, if we actually do the minimization in step 3, that is a well-defined supervised learning procedure. That thing will converge. It won't converge necessarily to a good policy. It'll converge to a Q function that's close to these targets. So if we think about how that's a perfectly well-defined and stable regression problem, we can maybe take a lesson from that and see if we can import that lesson into the more online algorithm up top to get it to be a little bit more stable, to get it to suffer less from this moving target problem. So here's what we can do. We can introduce something called a target network. I'm going to just sketch out the algorithm, and then I'll explain how it relates to fitted Q iteration. So in this algorithm, we're going to again collect our data from some policy, add it to your buffer. Then in an inner loop, we sample a batch from the buffer. And then we take a gradient step like before, but there's an important difference. The difference now is that when we compute our target value over here, we don't use Q phi, we use Q phi prime. What is phi prime? Phi prime is some other parameter vector. So that means we're changing the parameters phi, but we're targeting a target value that depends on some other parameter vector phi prime, which means that changing phi does not change the target values. So now this step does correspond to regular regression. There's no moving target anymore because I've changed this phi to a phi prime, to some other parameter vector. Now, of course, you're going to say, well, you can't just choose any phi prime. That would be stupid, right? If you just choose some random phi prime, then you get garbage target values. So it's a well-defined regression problem, just not a very useful one. So you somehow have to choose phi prime so that Q phi prime is still a pretty good Q function. So where can we get a pretty good Q function? Well, we can just use the Q function that we had 10,000 steps ago. So what we do is we do this k times, we go out and collect more data, and then we have this outer loop where fairly rarely we'll actually update our phi prime to be our current phi. And we do this much less often so that most of the time this inner loop is not trying to hit a moving target. Most of the time this inner loop is regressing onto targets that remain stationary, but then periodically, roughly every 10,000 steps, we go out and actually update our target values so that they are actually decent target values. So this is Q-learning with a replay buffer and a target network. And now this inner thing looks a little bit more like that supervised regression, that minimization that we had in fitted Q iteration. So targets don't change in the inner loop. Okay, and this looks more like supervised regression. So now that we've introduced these pieces, we can actually put them together to get kind of the classic deep Q-learning algorithm called DQN. So that's basically exactly the algorithm I've outlined so far. It modifies online Q-learning with 2 additional ingredients, using a replay buffer to decorrelate samples, and using target networks to avoid having to hit a moving target. And that's basically it. The classic, deep Q-learning algorithm is basically an instantiation of this where we set k to 1 and set n to 1. So you take some action and observe a transition, just like an online Q-learning, but you don't actually use that transition for training. You just put it in your buffer. Then you sample a mini batch of some other transitions from your buffer. So even though you just collected this transition here, that's not what you're going to be using to train. You're going to be sampling something else. You might get lucky and randomly sample the one you just got, but usually not. Usually you'd sample some older stuff. Then you compute your target value, but you don't use q phi, you use q phi prime for your target value. And then you take a step on the gradient, on the regression gradient. And then there's a step 5, which you only execute every large number of steps, like let's say every 10,000 steps, which is that you copy your phi into phi prime. So this structurally looks quite a bit like online Q-learning, with two very important differences. One is that you don't actually train on the transition you just collected, and the other one is that you use this target network. And these two changes actually substantially stabilize the Q-learning process. OK, questions? Yes?
So, but now the target is still moving. It's just moving less frequently. Why does this work?
Yeah, so the question is, the target is still moving, it's just moving less frequently. Why does this work? Well, the answer is that sometimes it works and sometimes it doesn't. So if before it never worked and now you update it every 10,000 steps, maybe it'll work 9,999 times out of 10,000. So it's not a bulletproof fix. It's a heuristic solution to a very intractable problem. Yes?
How do you do with sort of like initiating the target network parameters? Because in the very first try, if your weights are terrible,
Yeah.
you're regressing against a terrible target.
So the question is, well, how do you initialize that target network? Because if initially your weights give you a terrible Q function, then you'll just learn to regress onto terrible Q values. It's kind of a delicate question. In practice, initializing the parameters randomly is perfectly reasonable. The detail is that typically you would use an initialization such that your initial Q values are small. So when your initial Q values are small, then the target is mostly dominated by the R, not by the max Q. So initially, you'll just essentially learn to copy the reward into your Q function. And that's actually a pretty reasonable initialization. Any other questions? Yes?
So you're missing a square over there, right? The Q minus Y part, or it's not common?
So this doesn't mean take the derivative of this. This literally means the derivative of Q with respect to phi.
Okay.
So this quantity is the derivative of Q minus Y squared. I've just written out the derivative for you.
Oh, I see, yeah.
OK. So you'll implement this in homework 3, hopefully correctly. All right, let's talk a little bit more about these target networks. There's a little subtle design decision here that we have to make. So let's talk about the step 5. And I think the question earlier kind of alluded to this. So let's kind of imagine this process. We collect a transition, we update our phi, we collect another transition, we update our phi, collect a transition, update the phi, et cetera, et cetera, et cetera. And the target value that we use, for example, to update the phi on this step is obtained from the value of phi at this step. So let's say that our lag is 3. Usually our lag will be like 10,000, but let's just say it's 3 because I don't want to draw 10,000 things on the screen. So if it's about 3, then maybe over here you grab your target values from this phi vector. Over here you grab them from this phi vector and so on. Over here you grab them from over there. And then let's say on this step phi got updated. So on this step right here we've set our phi prime to phi. So that means that on the next step we're actually grabbing it from the step immediately preceding it. So we had no lag, a little bit of lag, a lot of lag, and then no lag again. So this seems a little strange, like we have this sort of very, very bursty level of lag where it increases, 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 then drops to 0, then increases again. So we might find this a little bit aesthetically displeasing. If you find it aesthetically displeasing, there's an alternative you can use that will keep the lag the same always. And that alternative is very similar to something called Polyak averaging. So if you've heard of Polyak averaging and convex optimization, kind of a similar principle, instead of actually updating phi prime to be equal to phi every 10,000 steps, what you can do is you can update it every single step, but have a damping term on it. So you basically set the new phi prime to be the old phi prime times some constant tau plus 1 minus tau times the new parameter vector. So if you use, let's say, tau equal to 0.999, then 0.1% of the numerical magnitude in phi prime will come from the latest parameter vector, and the rest will come from the old parameter vector. So this basically forces phi prime to be a kind of a damped version of phi, a time-averaged version, which in practice behaves quite similarly to the target network from before, but without this perhaps aesthetically displeasing bursty property where it's updated at very discrete points in time. So it's updated every time, but with a damping parameter that ensures that it changes much more slowly than the actual parameter value phi. Okay. So this is just a little modification you could use if you feel so inclined. All right. Now, we can actually relate this algorithm that we just derived to fitted queue iteration. They're actually very, very similar. In a sense, this process is basically fitted queue iteration, but inside out. So in fitted queue iteration, I had it written as a minimization before, but you can equivalently write it like this, where you have the target network updates in an inner loop. Here they're in an outer loop. So this deep queue learning thing is basically just fitted queue iteration, but kind of inside out, with the target values being updated less often and the data being collected more often. So looking at these two things side by side, we might kind of think that, well, maybe there's sort of a generalization of all this that doesn't have a bunch of nested inner and outer loops, but something that just recognizes the fact that there are multiple concurrent processes going on in this algorithm. And we can actually sketch out a diagram like this that avoids weird nested loops and shows this method for what it really is, which is a collection of multiple concurrent processes. So here is the more general view. The more general view is that you have your data set of transitions, and you have one process that goes out and fetches data. So I'm going to call this process 1. This is the data collection process. If you're learning in the real world, maybe you have an actual robot or website or something that's like actually interacting with some physical thing. That's process 1. It goes out and collects data, and when it has to go out and collect data, what does it do? Well, it grabs whatever your latest queue function is, augments it with a little bit of exploration, maybe some epsilon greedy heuristic, goes out and fetches some transitions, and puts them into the buffer. Now your buffer will fill up, so you need some other process that will evict old data. A very common choice is just use a FIFO queue, basically use a ring buffer where once it fills up, it just overrides the oldest entry. So you can think of it as an eviction process that just evicts whatever is the oldest thing in the buffer every time you add something to it. So this ensures that your memory requirements don't grow out of control. Then you have another process, which is the process that updates your target parameters. So this is a much slower process that will grab your current parameters and just copy them into the target parameters. Or it might do this polyac averaging business every single step. So your choice what you do there. So that's process 2. And then process 3 is the actual training process. The training process fetches data from the buffer, fetches the target parameters, uses them to update the current parameters, and that actually updates your queue function. And now you can see how these three processes can be treated as just three concurrent things that we can speed up or slow down however we want to obtain different versions of this algorithm. And of course, you could actually implement this as a completely parallel system. And if I have a little bit of time at the end of the lecture, I'll actually show you an example of some recent research that does that. So this is kind of the general concurrent view of this fitted queue iteration, of which all the algorithms we've discussed so far are special cases. Okay, so the online queue learning algorithm from last lecture is a special case of this where we evict immediately, meaning like we only ever store one transition in our buffer, and then process 1, process 2, and process 3 all run at the same speed. So they all get updated all at once. The DQN thing, which is what you're going to be implementing for homework 3, process 1 and process 3 run at the same speed. So for every transition you collect, you take one gradient step, and then process 2 is very slow. And your buffer is of size larger than 1. And then fitted queue iteration, kind of the classic fitted queue iteration, process 3 is actually in the inner loop of process 2, which is in the inner loop of process 1. So that's just another variant on the same recipe. All right. Does anybody have any questions about this? Yes?
So if you're just evicting the oldest thing, like what if you were exploring more in the beginning or something?
Yeah, so the question is, well, I said they should evict the oldest thing. What if you had some really good exploration policy in the beginning, and now towards the end you're mostly just kind of exploiting and you're not really visiting diverse states? Maybe you should actually keep some of that older data. And that is actually the case sometimes. So you might actually find in homework 3, for example, if you dial down your exploration, if you dial down the epsilon and epsilon greedy a little too fast, you might end up with a buffer that's full of very similar data, and you'll actually see that your policy improves, and then crashes once the buffer fills up with that very deterministic data. So there are a few tricks to deal with this. In practice, what people prefer to do is, instead of being clever about what to evict, they just use a bigger buffer, because RAM is cheap and coding time is expensive. But in principle, you could also be more clever about it. Yes?
So aren't all three technically using like a deep queue network? So why is only one algorithm called that?
So the question is, aren't all of these things potentially using a quote-unquote deep Q network? So why is only one algorithm called that? Branding. You know, DeepMind needed to sell their company to Google, so they needed to put a brand on it. Any other questions? Yes?
If correlation is the problem in sampling the data, have people tried having some smarter sampling strategy?
Yeah, so the question is, if correlation is potentially a problem for this, have people tried smarter sampling strategies? In fact, yes. There's, for example, a paper that you could read called Prioritized Experience Replay, which tries to sample data from the buffer in a smarter way, actually prioritizing samples where the current Q function makes the largest mistakes. And you can get some speed up and some performance gains from doing that. OK, so at this point, I'm about halfway through the lecture, so I'll take a break. And we'll be back at 10:47 to continue our discussion of Q learning in practice.
Question. So basically, like this model is like tracing a target, and then I can convince that like it can reach the target, it can converge, but like whether it would converge to a good place, because that doesn't tell any.
Yeah. So the deeper issue with all this is that, you know, Q learning, no matter how you frame it, the whole Q learning process is not gradient descent. So even in the tabular case, it's not gradient descent. In the tabular case, it's fixed point iteration, right? So that's why we need to show that it's a contraction. The way that you can actually argue why deep Q learning algorithms can converge is by appealing to the power of that function approximator. So the non-convergence issues are due to the fact that your projection is not perfect, right? Your projection doesn't perfectly match BQ with Q, but if you have a very, very powerful function approximator, you might imagine that the error might be very, very small. So if you have some, you know, if you're doing like linear regression, then you'll have a very bad fit to your target values. If you have a giant deep net, you might have a very, very good fit. So now, even though the composition of that L infinity contraction and that L2 contraction is not technically a contraction, the L2 projection is an almost perfect projection. So perhaps you can kind of pretend like that part doesn't actually matter. That is basically close enough to a table as to be almost perfect. So that's the real reason why deep Q learning actually has a chance of working. Is that it's a projection, but potentially a very, very good projection.
Like, if that's the case, that it can converge because you like somehow degenerate to this kind of problem that these two distances like smaller enough the difference.
Yeah.
How can I be convinced that they converge to a very good place? Like that learns a very good policy. Because
yeah, that's a difficult question. People have analyzed a little bit how close the fixed point for a function approximator is to the optimal policy for the case of linear function approximators. And there's a little bit of literature on this. The trouble is, of course, that linear function approximators are not very expressive. So that's arguably not the regime in which deep Q learning operates. So beyond that, it's kind of all open problems.
I have a question on the convergence thing that we
Yep.
talked about on Monday.
Yep.
So I have hastily scrawled business here, but there's this inequality where if you have a norm in LP space, it's less than or equal to a norm in R space where R
Okay.
is less than P. So why can't you take this 2 norm, upper bound it by the infinity norm because of this, and then just take the entire expression, bracket these. You know that from this fact. Now you've got this in the infinity norm, and that's bounded from here, so the whole thing's contrasted.
Well, but then you have a 2 norm here bounded by an infinity norm here.
Oh, I see. And so you need this to be an infinity norm?
Because you have to iterate it. Yeah, unfortunately, there's no algebra trick that will cause a composition of a infinity norm and a 2 norm to be a contraction in general.
I see.
I wish there was, because that would make my research a lot easier.
Fair enough. Okay.
All right, let's resume. So before the break, we saw how we could design deep Q learning algorithms and some tricks that we could use to actually make them work. And we've actually already covered what you guys need to implement the basic version of deep Q learning for homework 3. So now let's study some questions about deep Q learning and learn about some tricks that we can use to make it work even better. So the first question we're going to ask about Q learning with deep neural networks is, are the Q values accurate? Right? When we introduced the Q function, we defined it. The Q function has a meaning. It is the expected reward that you will get if you start in a particular state take a particular action, and then follow your policy pi. So it's a prediction. It's a numerical prediction about your future reward. So do these deep Q-learning algorithms learn accurate predictions? So let's look at a little bit of evidence. These are learning curves for two Atari games, Breakout and Sequest. The two plots on the left show the actual returns obtained on Breakout and Sequest by a Q-learning algorithm with a deep neural network. And this looks decently good. The rewards are going up, which means that you're doing better. You're doing a bit better on Breakout than you are on Sequest. Sequest is a hard game, but they're both going up. That's great. That means that we're learning to play the game. The two plots on the right show the average action Q value, right? So the average Q value of the actions that you actually take. And those are also going up. That's good. You're doing better, and your Q function believes that you are doing better. That seems very reasonable. We can look at what happens at different points in time in an actual episode of the Breakout game. So for those of you that don't know how Breakout works, there's a little pink paddle here. It moves around left to right. There's a ball that comes down. You have to hit the ball with the paddle, and then it bounces up and hits these bricks. And the goal is to break the bricks. So it's sort of a very anti-establishment sort of game. You have to destroy all the barriers. Very appropriate for Berkeley. So you can look at the value function, and you can see peaks in the value function. This is just computed by taking the max over the actions. You can see the value function peaks when the agent expects that something good will happen. So over here, it's about to break a brick. There's a little tiny peak in the value function. Over here, there's a little peak. Over here, it's about to break some more bricks. There's a bigger peak. And then over here, breaks through the wall onto the other side. And it really likes doing that because that means the ball could bounce around here a whole bunch and it can get lots of reward. And it's really happy over here. It thinks like, now my value function is high because I'm anticipating getting lots of reward in my imminent future. So that makes sense. That means that we're learning some kind of prediction that is actually reasonable. We can look at the Q values for different actions. So this is basically, these three bars show the Q values at the same state but for different actions. So this one is for doing nothing. This one is for moving the paddle up. This one is for moving the paddle down. This is the game Pong. So Pong, you can kind of think of it as basically table tennis, but for an Atari game. So you control this green paddle, and you move it up and down. And you can see that over here, the ball is a little ways away. So the Q values for all the actions are actually about equally good because it thinks, even if I don't move towards the ball now, I'll still have time to catch it later. So it doesn't matter what I do. Over here, the ball is closer to crossing the line. So now here it says, going up has a much larger Q value than the other actions, meaning that if I go up, I might still catch the ball. But if I don't go up, then I'm going to be in trouble. And then over here, it hit the ball back, and it's about to score a point on the opponent. And here the Q values are all good because it says, it doesn't matter what you do. You're about to score a goal anyway. Just let it go. So that all seems reasonable. But are they actually numerically accurate? So this plot studies that question. Ignore the blue stuff for a second. I'll explain the blue stuff a few slides from now, and only look at the red stuff. The red curve here, this shows the estimate of the Q value from the Q function neural network. And the solid red line shows the actual reward that the agent got. And you can see that on all four of these games, the anticipated reward is actually much, much larger numerically than the actual reward obtained by the agent. This doesn't contradict what we saw here. They're both going up, the actual reward and the anticipated reward. It's just that numerically, the predicted reward seems to be systematically much bigger. Just the numbers are bigger numbers. They still correlate with the right outcome, so worse actions have lower numbers, better actions have bigger numbers. It's just that all the numbers are too big. Why are all the numbers too big? Why is our Q function such an optimist? Why does it expect more rewards than it's actually going to get? Does anybody have any hypotheses? Yeah.
Maybe using an old target network makes it like bigger rewards.
Maybe somehow using an old target network gives you bigger target values. That could be. It could be if you initialize your Q function to really big numbers, then the target values will be systematically too big. But usually we initialize our Q function to small numbers. Here's the trouble. let's imagine that we have a signal. So we have a signal like this. That's our true signal. I'll draw it like that. So this true signal has a maximum right up here. And I have a function approximator that tries to fit this signal, and that function approximator is corrupted by noise. So the noisy fit looks like this. And now what I'm going to do is I'm going to try to find the max of my noisy approximation. The max of my noisy approximation is probably somewhere over here. It's on the x-axis, it's pretty close to the true max, so this distance is small. But the max of my noisy function is always going to be bigger than the max of my true function, right? Because if my noisy function is a true function plus noise, when I try to find its max, I'm maximizing the function and the noise. So I'll always pick a point where the noise actually makes it seem bigger than it really is, provided such a point exists. That's the basic intuition behind why Q-learning overestimates. So let's try to make this a little bit more concrete. So your target value is calculated by taking your reward plus gamma times the max over the actions at the next time step of your estimated Q values. So it's this max that's the problem. Imagine that you have two random variables, x1 and x2. These random variables, you can think of them as, for example, the values of this noisy function at two different points. Or in the case of Q-learning, they're the Q values for two different actions. You can show very easily that the expected value of the max of x1 and x2 is always greater than or equal to the max of their expected values. That basically says that if you take the max of two noisy numbers, you'll maximize, you'll basically pick the one that's bigger plus the noise. And that will always give you a bigger number than the max of their expected values. That's the same as why here the max of the noisy function was always bigger than the max of the true function, provided that it's noisy enough. So that's the basic intuition for why this last term overestimates. If you imagine that your Q is not perfect, it kind of looks noisy, meaning that for different actions there's some imperfection, some error, which we can crudely model as just random noise. Then when you take the max, that's just like taking the max of two random numbers, which is systematically larger than the max of the underlying noiseless signals, their expected values. So when you take the max, you'll always overestimate the next value. Basically, if there is some action for which you have error, and that error makes it seem better than it really is, you'll pick the one with the biggest error. Another way to think about this is to write out the max like this. This is kind of a silly way of writing the max, but it will help us understand what's going on. So the max of Q with respect to A prime is just the Q evaluated an action given by the argmax. Kind of silly because I had something short and now I write it out and it's much longer. But this might give us a hint about what's going on. So the argmax will pick the action for which the Q value is erroneously high, if such an action exists. And then you'll just grab that action's value, which is the one that has the error in it. So that's why you'll tend to overestimate. So you select the action according to Q phi prime, and your value also comes from Q phi prime. So the noise in those two is correlated. So let's try to fix this problem. The problem inherently is due to the fact that the same noise affects the argmax and the value. So what if we could somehow decouple these? What if we could somehow have, we can't have a perfect noiseless Q function because errors will always be there, but what if we can somehow get the numerical value in the Q function to have different errors than the argmax? So if we can somehow decorrelate those errors, the problem goes away. So here's the idea. What if we don't use the same network to choose the action as the one that we actually use to calculate the value? So what if we have one network that we use for the argmax and a different network that we use to evaluate the actual value for that argmax? That's like saying that I have two noisy signals, the original one I drew here, and then another one that has different noise. So if this dotted line is the one where I take the argmax, maybe I plant the argmax right here, and then I get the value from the solid line, now I don't overestimate anymore. because the errors in selecting the position on the x-axis, which is the action, is decorrelated from the errors in this direction. So this will help me mitigate the problem. So the way that I can do this, it's called double Q-learning. Use two Q functions. So one Q function is going to be phi a, the other one is phi b. Phi a will be updated by using phi b for the values, but phi a for the argmax. And phi b will be updated by using phi a for the values and phi b for the argmax. So you never evaluate a Q function at an action which is the argmax of that same Q function. You always take the argmax with one and the value from the other. This ensures that the values are decorrelated from the errors. So if phi a and phi b really have independent mistakes, if they're basically both roughly equal to the true values plus independent noise, then this would actually get rid of the overestimation problem. Okay, that's kind of nice. So now, of course, we have to implement this as a practical deep Q-learning algorithm. So where do we get the two Q functions? We actually don't have to change very much in our existing algorithms because our existing algorithms already have two Q functions. They have a Q phi and a Q phi prime. So all we have to do is slightly modify the algorithm we already have so that it never evaluates the value at an action which is the argmax with respect to those same values. So just use the current and target networks as phi a and phi b. And then before you had your standard Q-learning where you plug in Q phi prime and then the argmax with respect to Q phi prime. Now just change that phi prime to phi. So you can actually implement double Q-learning just by modifying your target value calculation in one very, very small way, which is to remove that phi prime and replace it with phi. So now you take the argmax with respect to the current network, but then plug it into your target network to get the actual numerical value. Now, of course, this is a heuristic because the phi prime and phi aren't actually independent. In fact, if you just updated phi prime to be equal to phi, they're anything but independent. But in practice, they're decorrelated enough such that this thing does, to a large extent, mitigate the overestimation problem. So all you've changed is change that phi prime to a phi. So just use the current network instead of the target network to evaluate the action. Very, very small change. And it actually ends up doing a lot to improve the performance of Q-learning by mitigating this overestimation issue. OK. Does anybody have any questions about double Q-learning? Yes?
Well, since the goal for this Q-learning is to find a good policy, why do you care so much about the value?
Yeah, so the question is, well, since the goal of this whole thing was to find a good policy, why do you actually care about the numerical magnitude of the value? The answer is we don't actually care about it. But in practice, when the values are incorrect, you tend to get a slightly worse policy. The policy can still be decent, but making this change does make the policy better. Yes?
Do you still update phi prime in the way we did before, or do we?
All right, the question is, do you still update phi prime the way that we did before? Yes, everything is exactly the same. Literally, the only change I made is I removed the little prime symbol there. In fact, you'll actually implement this for homework 3, and it'll be as easy as it sounds, hopefully, yes.
Doesn't that make y somehow correlated with phi?
Right, so the question is, well, before, the whole reason we put in this phi prime thing was to decouple phi from the target values, and now we've just gone and coupled them again. So, well, I mean, what can I say? Deep RL works in mysterious ways. Any other questions?
Has anyone actually done an analytical analysis, like how much this is going to decouple and then ruin our previous assumption?
Right. So how much does this decouple? It's hard to quantify what decoupling really means because it's such a vague term. People have quantified how much this reduces overestimation, and the answer is that it reduces it a lot. So the picture that I had before, we can actually go back to that and take a look. So here, the red curve is what you get from regular Q-learning. The blue one is from double Q-learning. So you can see that it's a night and day difference. It's gone from overestimating massively to actually being pretty damn close. Yes, back there.
Why is overestimation such a bad thing? Is it just off by like some scale?
Right, so the question is, why is our overestimation bad? Is it off by just some scalar? Well, the answer is that it's not off by some scalar. It's actually just incorrect, and it's always incorrect in the same direction. So if the issue was that your values were always bigger but the relative actions were the same, then this wouldn't be a problem. In practice, that's not the only problem. The intuition for why that would be the case is that your rewards are still on the same scale. So your target values are reward plus the next Q. The rewards don't go up, only the Qs do. So therefore, you end up not paying as much attention to the rewards as you should because your Qs are bigger than they should be. Was there another question? Okay. Yes?
Why don't we just have two target networks?
Why don't we just have two target networks? We could. You could try implementing that for homework 3 too. It'll work decently well. It's just that then you have 3 networks total instead of 2. The nice thing about this way of implementing double Q learning is that in homework 3 this will be a one-line change. Actually less than one line. It'll be like a piece of one line. It'll be, depending on how long your variable names are, it might be a one-character change. Whereas introducing a whole other network would be a much larger change. So it's purely a simplicity thing. All right. Let's talk about another improvement that we can make to deep Q learning, and that's multi-step returns. So let's bring up our Q learning target calculation again. Where does the signal in this target come from? The target consists of 2 terms, and we add those terms together. It has a reward term and a Q function term, right? So the target values, the Q function terms in the target values are going to be pretty big if you have a discount of like 0.99 or something, and you've learned a good Q function. If you learned a good Q function, you'd expect the second term in that sum to be bigger than the first term, and therefore you'd expect that second term to really dominate. So when you update your Q function later on in training, once your Q function estimator is already pretty good, most of your learning is coming from that second term because that's the bigger term. But if your Q function is terrible or random, then most of your signal comes from the first term, right? So if that second term is a small random number, essentially, all you're really learning is the information that's contained in that reward. This might seem a little bit unfortunate because the reward, the first term only gives you the reward for one time step, and you'd like to learn how to behave intelligently for many time steps. So early on in training, when your Q function is bad, you're only learning about the stuff that's contained in this number, and this number is only the reward for one time step. So you're kind of not learning very much. In fact, you have to wait for a little while until this second number gets close enough to the true Qs before you actually start learning more than one-step rewards. Can we do better? Well, we've been in this situation once before. We were in this situation in the actor critic lecture when we saw that an actor critic update, where you do the reward plus the next value minus the current value, has lower variance, but it's a bit biased, meaning that if your value function is incorrect, this is not really a good estimate of your advantage. In the same way up here, if your Q function is incorrect, this is not a good estimate of your target value. Before that, we had another way to estimate returns, which was to use Monte Carlo sums. That's what we used in the basic policy gradient algorithm. And we saw that these things have no bias, but they have higher variance because they're essentially single sample estimators for some gigantic integral. So we saw in the actor critic lecture that we could trade off these two things by essentially interpolating between these kinds of low variance biased estimators and these kinds of unbiased high variance estimators. And we saw that we could do this by summing together rewards not for all time steps, but for a few time steps, and then putting the value function at the end. We can do the same thing with Q learning. So we can construct what's called a multi-step return or n-step return, just like we did in actor critic. So that amounts to a different equation for the target value. In this new equation, we sum the rewards that we actually saw from the current time step until t plus n minus 1. So we choose some value of n, maybe we choose n equals 10. So we'll sum together 9 different rewards, and then for the 10th one, we put in our Q value at that step multiplied by gamma to the n to account for the fact that it's now n steps into the future rather than 1 step into the future. So why might we prefer to do this? Well, if our Q function is currently not very good, if it's essentially a small random number, then we're summing together more than one reward, which means that we're getting a little bit more learning signal out of this. If your Q function is already pretty good, this will have somewhat higher variance, but if you choose kind of an intermediate value of n, somewhere between 4 and 10, let's say, then this might give you a pretty good balance. And in general, there's kind of no reason to expect n equals 1, which is what you have for classic Q-learning, to be the optimal choice. So by increasing n a little bit, you might be able to get a little bit more performance, especially early on in training. Can anybody think of a problem with this n-step estimator? Yes?
Is it on policy?
Is it on policy now? I don't know, is it?
Well, because now your rewards are coming from however that rollout did.
Right. So your rewards here came from some trajectory. So your target value, in the extreme case, let's say n goes to infinity, you just have a Monte Carlo target value. That's not the value of your current policy, that's the value of whatever policy collected that data. So Q-learning was great because Q-learning was an off-policy algorithm. We didn't care which policy collected that data. Now we suddenly do care because that sum, in the first terms, the sum in the first term, estimates the return for a particular policy, specifically whatever policy collected that data. So now we're not really off policy anymore. So you have a less biased target value when your Q values are inaccurate, typically faster learning, especially early on, but it's only really correct when you have on-policy data. Why is that the case? Well, for the reasons that we just discussed. Now, you might kind of argue this is not so bad because if you assume that your policy is getting better and better, then you might surmise that any old policy is no better than your current one. So at worst, these values will be pessimistic rather than optimistic. So if n-step return speeds up learning, the pessimism slows it down, maybe it kind of balances out. OK, so to really make this correct, you need transitions that actually come from your latest policy. Not an issue when n equals 1, because when n equals 1, it's just the first reward, and the Q function is conditional on the first state in action, so that doesn't matter. But for n greater than 1, it does matter. How do you fix it? Well, you can ignore the problem. For small values of n, roughly n equals 4, ignoring the problem tends to work pretty well. You can cut the trace, which means that you can adaptively select n. There are a few ways to do this, but one of the things you could do if you have, let's say, a small discrete action space, maybe you're playing Atari games and you just have 3 different actions, what you can do is you can actually choose n to be, let's say, some number between 1 and 10, let's say the largest number between 1 and 10, such that all of the steps up to n take the same action that your current policy would have taken. Now, that's pretty unlikely, but if you have a small action space, maybe you'll get lucky and you'll find enough chunks that take exactly the action you would have taken anyway that are of length greater than 1. You can do even better than that. You can do all sorts of tricks to try to increase that length. And if you want to learn more about that, I suggest checking out this paper called Safe and Efficient Off-Policy Reinforcement Learning by Munoz et al., which discusses some tricks involving some importance sampling and things like that to allow you to essentially dynamically select how long to go when you sum together those rewards. Yes?
Why don't we discount the rewards in the first sum?
Why don't we discount the rewards in the first sum? Because I made a typo in my slide. So let me write the correct equation. Thank you for catching that. So the correct equation should be this. Sum t prime equals t to t plus n minus 1 of gamma to the t prime minus t times rt prime plus gamma to the n max, etc. Right? So this is the term that I'm missing in my slide. Please take note of that. OK, Q-learning with continuous actions. So so far, we've kind of brushed under the rug how we actually calculate that max, because we just assume that for discrete actions, you just enumerate Q values for all possible actions and take the largest one. So that's how you can get a max or an argmax. In continuous action spaces, of course, this is not so simple. So with continuous action spaces, the problem is this max. It typically cannot be evaluated exactly because you have, of course, infinitely many actions. So you have a number of different choices if you wanted to use Q-learning in continuous action spaces. Before I tell you what these choices are, does anybody have any suggestions, any ideas for how we could implement Q-learning with continuous actions? Yeah?
You can try to predict the parameters of a distribution.
Predict the parameters of a distribution and do what?
Of an action.
Can you elaborate on that?
So you can try to predict the distribution of the probability of the action you should take.
Mm-hmm.
And then, for example, Gaussian,
Mm-hmm.
you can predict the mean and the variance or multi-Gaussian.
Okay, yeah, so the answer is that if you can figure out an action distribution, kind of like an actor, and maybe you choose some distribution where it's easy to find the peak, like a Gaussian, some kind of unimodal thing, then maybe you can use that as an approximation for the actions, for the Q values of function of action. We'll actually see a method that does something a bit like that, yes.
You could just sample a bunch of actions and max that.
You can just pick a bunch of actions, just a discrete set of actions, and just take the one with the biggest Q value. You could do that, yeah. We'll actually see something like that too. Any other ideas? Okay, that's good. Well, let's see what I have on my slides and see how much that agrees with what you guys were thinking. Okay, so you need to do this max. It's not just the max in the policy. The max in the target value is arguably more problematic because it's in the inner loop of training. So you don't want some really expensive optimization procedure for this. So the first option that I'll talk about is the optimization option. So the optimization option basically says, let's use some optimization procedure to calculate this max. You could do like gradient-based optimization. You could literally like run gradient descent on A. It's not a very good idea because you have to do it in the inner loop of training to calculate your target values, and that tends to be pretty slow. So in practice, there are other ways of doing that optimization that can be a little bit more manageable. So there are a few things we can exploit to make this optimization a little faster. One is that the action space is typically low dimensional. So parameter spaces for deep neural nets are typically huge. You might have like millions of parameters, but action spaces are usually not that huge. You can of course imagine some tasks where you have very large action spaces, but if you're like controlling a car, for example, maybe you have 4 continuous numbers that you have to output as actions. So it's not that big. So that allows us to use fairly simple stochastic optimization methods, one of which was the one that was mentioned by the student previously, which is to just approximate the max by a max of a discrete set of actions. So basically just pick some actions at random, pick n of them, evaluate the Q value for all of them, and just take the best one. That is an optimization algorithm. It's not a very good optimization algorithm, but let me tell you, it's really fast, and it's really easy to implement. And if your problem is overestimation anyway, maybe you don't need to optimize so hard. Maybe just a little bit of optimization will do. But it's actually very easy to improve on this method, building on the same building blocks. So this one is nice because it's dead simple and efficiently parallelizable. It's not very accurate, but do we really care? How good does the target need to be? If you do want it to be better, you can use something called the cross-entropy method. The cross-entropy method is something that we will cover in a subsequent lecture, but the high-level idea behind the cross-entropy method is sample a bunch of actions, evaluate their values, but then instead of simply taking the biggest one, what you do is you fit a distribution to the best ones and then sample again from that distribution. So the kind of intuitive model of cross-entropy method sample some values, evaluate their numerical score, fit some distribution to the best ones, sample some more from that. So you get some that are like this. So every time you sample, they get better. Fit another distribution, sample again, and so on. So we'll see this method in a little bit more detail when we talk about model-based reinforcement learning later. But in the meantime, if you do want to give this a shot, look up cross-entropy method. It's very easy to implement. You can implement it in about 4 lines of Python code. You can do other fancier stochastic optimization techniques, CMAES, etc. So there are a lot of choices here. We'll talk about these kinds of optimizers more when we discuss model-based reinforcement learning in a subsequent lecture. Okay, and this kind of stuff tends to work okay for dimensions of about, like, let's say 30 to 40. If you have actions that are higher dimensional than 40, maybe this is not such a great idea. There's another way to do it, option 2, which is to use function classes that are themselves easy to optimize. So if you have a neural net that takes in the state and the action and outputs the Q value, there aren't really very convenient ways to optimize with respect to the action, except for using some gradient-based thing or some stochastic sampling thing. But there are actually other function approximators you could choose for which it's possible to analytically calculate the max. One such function approximator is a quadratic function. So if you have a quadratic function, figuring out the optimum of the quadratic function is pretty easy. You just do it by solving a linear system. Of course, you don't want to have a quadratic Q function that's quadratic in the state and action. That would not be very expressive. But if you imagine that you have really complicated states but relatively simple actions, perhaps what you can get away with is a Q function that's quadratic in the actions, but arbitrarily nonlinear in the states. So you can represent your Q function, for example, as basically a quadratic form where the matrix and the vector in the quadratic form are produced by a neural network. So you have a neural net that outputs a vector mu, a matrix P, and a scalar V, and then the Q value is given by A minus the vector, transpose times the matrix, A minus the vector plus the scalar. So for this thing, the action that gives you the largest Q value is just mu. So you have a Q function estimator that is quadratic in the action, but arbitrarily complex in the state. Okay? This particular thing is called normalized advantage functions. It's pretty simple. Your argmax is just mu. Your max is just v. There's no change to the algorithm. You don't have to implement any fancy optimization. It's just as efficient as Q-learning, but it has a pretty substantial downside, which is that your Q function now has to be quadratic in the action, so you lose some representational power. If your actual real Q function is highly non-quadratic in the action, then this thing might not do very well. But if you have a system that has relatively simple actions but complex states, this can be a very convenient way to do Q-learning with continuous actions. All right, and last option. The last option is kind of an interesting one. It's kind of like the optimization option, only instead of performing optimization independently each time, you're going to actually learn another network that performs the optimization for you. So the particular algorithm I'm going to describe is called DDPG by Lillicrap et al. From ICLR 2016. The paper, if you actually look up this paper, it presents the method as a deterministic actor-critic algorithm, but you can also interpret it as a kind of approximate Q-learning algorithm. So here's the idea. Remember how we could write the max of the Q function as the Q value evaluated at the argmax. Now here the hard part is the argmax, because if you have a continuous action, evaluating the argmax is hard. So what we'll do instead is we'll train another neural network that we're going to call mu of s, such that mu of s approximates the argmax. So mu of s outputs an action, and it's trained so that that action is as close as possible to the argmax of the Q function. How do we train it? Well, all we have to do is we have to solve this optimization problem. We have to figure out the parameters theta of mu that are the argmax of Q of phi of s comma mu theta s. This just requires pushing gradients through the Q function, and we know how to do that. We can just do that via the chain rule. So the derivative of the Q function with respect to the parameters of mu, so dq d theta, is just dA d theta, which is the derivative of mu with respect to theta, times dq dA. So if both mu and q are neural networks, you can calculate both of these derivatives. In fact, any automatic differentiation package will actually do this for you automatically. So it's pretty easy to perform this optimization. And now, when you calculate your target values, just plug in mu in place of the argmax. So what you really want is q phi prime evaluated at s and the argmax of q phi prime, and instead you plug in mu. So you take q phi prime at s comma mu of s. So essentially treat your mu as though it was an argmaxer, and you train it to be a good argmaxer by following this gradient. So it's kind of a deep learning solution to an optimization problem. Yes?
It's more of a Q-learning method, then why is it called policy gradient?
Right. So if you actually read this paper, it presents the method more from the standpoint of taking a policy gradient procedure and then taking the limit as the policy becomes less and less stochastic. It turns out that if you do this, you recover a method quite a bit like this. They actually end up being equivalent. Any other questions? Okay. So let's actually walk through the kind of the pseudocode for this procedure. The pseudocode looks a lot like the deep Q-learning algorithm that we learned about before. Step 1, take some action, observe a transition, and put it in your buffer. Step 2, sample a mini-batch from your buffer. Step 3, calculate your target values using your target Q function and using a target mu, so mu theta prime. Step 4, update your Q function, just like before. Step 5, this is a new step, update the parameters of your argmaxer, update the parameters of mu. So To update those parameters, you just use that chain rule that I had on the previous slide, d mu d theta times dq dA. Step 6, update phi prime, the parameters of the target Q function, and theta prime, the parameters of the target mu, of the target argmaxer, or the target actor, if you want to call it that. And you can do it using either the flip it every 10,000 times rule or Polyak averaging. And then repeat. So it's essentially the deep Q-learning algorithm from before, but augmented with the use of mu in place of the argmax, and this additional update that actually updates the parameters of mu. Yes?
Wouldn't it be better to like first train mu separately and then?
Right. So the question was, well, wouldn't it be better if we just train mu to convergence and then use it? You could actually do that. In fact, there's some delicate trade-offs between how much you update mu versus how much you update Q. But remember that Q is constantly changing. So if you want mu to keep up, you have to keep updating it somehow. Now you can probably play some clever games in terms of how often target functions get updated and so on. But in general, you do need mu to keep up somehow. Yes?
Is this essentially the same as when you talk about like have a mini gradient update inside for action?
Right. So the question was, isn't this kind of the same as that thing that I told you not to do, which is to do a little bit of gradient descent on the actions? It is essentially the same. You can think of it as gradient descent on the actions, only amortized over all the transitions, and the amortization is performed via a neural net. So instead of explicitly keeping track of the optimal action for every transition, all you're keeping track of is the parameters of that neural net, which is sort of amortizing the cost of doing that optimization. Okay. All right. So that's Q-learning with continuous actions. Any other lingering questions about continuous actions? Yes?
In step 5, is the A the particular action that maximizes this?
Right. So the question is, which A do you plug in? You plug in the A from mu. So this is basically the derivative of Q phi of S comma mu of S. Yes?
Could you offset the overestimation of the Q networks by not using like the actual action outputted by the policy, but like the noisy version of it?
Right. So the question is, can you offset the overestimation from your Q function by not plugging in a good action and instead plugging in a worse action, like for example, adding some noise to it? You absolutely could. In fact, later on in the course, we'll learn about maximum entropy reinforcement learning methods that intentionally produce policies that are more random than they should be, and part of why they work actually has to do with this question. But it's a somewhat nuanced topic, so I'll leave that discussion for later. Yes?
In step 3, where is the maximization over actions taking place?
Disregard that. It's a typo. Sorry about that. I fixed that typo on another slide, but I left it here. Yeah, that max shouldn't be there. That's just a typo. There's no max anywhere. No maxes anymore. Only gradients. All right. Some practical tips for Q-learning. So Q-learning takes some care to stabilize, and these tips will be important for what you guys will be doing for homework 3. So when you're implementing your Q-learning algorithm, make sure to test it on some easy, reliable tasks first to make sure that your implementation is actually correct. Because there's sort of, as with many deep RL algorithms, but especially with Q-learning methods, there's sort of two battles you have to fight. Did I implement it correctly? And then did I set up all the hyperparameters correctly so that it actually trains on my problem? And you don't want to fight those two battles at the same time. First, set up something where any correct algorithm will work to make sure that your algorithm is correct, and then test it on the real thing. It also can take a while for it to learn. So these are learning curves from actual Atari games, from this paper called Prioritized Experience Replay. And you can see that on some games, like you guys will be testing on Pong for homework 3, for example, it just goes up and it's pretty happy. On some other games, it does a bunch of crazy stuff until eventually it figures out what's going on, has some epiphany, and then it starts getting better. So be patient, don't be concerned or alarmed if at first things don't seem to be improving. Unlike supervised learning, where in the first few iterations you'll get massive improvement on your loss, in Q-learning you'll often not get massive improvement on your reward function until some time into this process, because you have to explore, you have to find the right transitions, and after that the Q function has to actually figure out what's going on in those transitions. So it can take a while. Large replay buffers tend to improve stability, so generally larger than you think it should be is a good rule of thumb. That basically makes the algorithm look more like fitted Q iteration. It helps to decorrelate those transitions. And it takes time, so be patient with it. Also, it can help sometimes to put things on a schedule, especially the exploration. So it might help to start, if you're doing, for example, epsilon greedy exploration, it might help to start with very large values of epsilon, so you're mostly exploring randomly. That makes sense because initially your Q function is so bad that it's not really helping you take better actions anyway, so you might as well just take random actions. But then over time you want to decrease that number because as your Q function gets better and better, it'll be better at putting you into those higher reward states where you'll see more useful transitions. Bellman error gradients can be pretty big, so oftentimes with Q-learning it's very helpful to either clip your gradients or use a loss that doesn't keep getting bigger and bigger further from the optimum, like a Huber loss. So a quadratic loss is basically a parabola. A Huber loss looks like the absolute value function with a little rounded dip at the bottom. And that makes sure that your gradients don't just keep getting bigger and bigger the further away you are from zero error. Double Q-learning helps a lot in practice. It's very simple, and there's basically no downside to it, so you should always use it. N-step returns can also help a lot, but they do actually have some downsides, so you should not always use them, but you should frequently use them. It's a good idea to schedule your exploration. If you're using SGD with momentum, it's a good idea to schedule your learning rate. If you're using something like Atom, that can replace that to some degree, but your mileage may vary. And then if you're actually evaluating and testing your algorithm, make sure you run multiple random seeds because Q-learning is a very stochastic algorithm, partly because of the exploration. So you run it 3 times, you'll get 3 totally different answers. So if you want to make sure that your algorithm is actually performing well, run it a few times and average the results. All right, so now that I'm out of time, let me just review. I talked about Q-learning in practice. I talked about replay buffers and target networks, which you can use to actually get a practical deep Q-learning algorithm. I talked about this kind of generalized view of fit Q iteration where you have multiple concurrent processes. I talked about double Q-learning, which you should always use, and you will use it in homework 3. I talked about multi-step Q-learning with continuous actions, which we can do with random sampling, analytic optimization, and a second actor network. And I talked about how you're going to all implement deep Q-learning in homework 3 and see it playing Atari games. So I have office hours after this in room 347 over there, and I'll see you all next week.
Sure. So I think if you make unreasonable assumptions, you can get